Good morning, sir.
Good morning. How are you?
I am fine, sir. And how are you?
I'll wait for a couple of minutes. It is 12 only.
Okay, sir. Okay, sir.
Anyway, you have any questions or comments to make? Usually, I try to recall what was done last time and then proceed with it. Okay.
Okay, sir.
There are about 5 students who have come. I'm just waiting. All right. Let me recall what was done by the time they come. I hope you are able to see the screen.
Yes, sir.
I will come back to this part, but before this, let me give you what is that we are trying to prove. That's the question. The question is that we want to prove this theorem 7.5. That is for 1 less than or equal to p less than or equal to infinity. LP with this norm P called LP norm and C0 with the infinity norm are Banach spaces. What is that you have to show? It's a Banach space. You have to show first of all it's a non-linear space and then you have to show it is completeness. We have already shown it is non-linear space. The second part of the question is that moreover, if 1 is less than p less than q less than infinity, then L1 is contained in LP and the LP is strictly contained in LQ, that is strictly contained in T0, that is strictly contained in L infinity. Okay, that's what the point is. Finally, the norm of XQ is less than or equal to norm XP. It's what is called Jensen's inequality for all x in LP. 1 less than or equal to p, less than or equal to q, less than or equal to infinity. This is the theorem. So let me go through some part of it. How do you show the inclusions are not strict? We have to take the example which I had explained to you last time. So let me come to that example and then come to the proof of the completeness. Okay. So I don't know where he has done it. He has done it somewhere. Okay. I'll put the screen on the top. What we actually show is this, the inclusions are proper. You use the harmonic series, that summation 1 by I is divergent or infinity. Okay. But 1 by I actually is in C naught because the sequence goes to 0, but it is not in L1. Similarly, you want to push this fellow into the LP, all right? So how do you show that? You show it to the, so instead of I raised to 1, you take it as I raised to 1 by p. When you take I raised to 1 by p, 1 over I raised to ip, when you raise this to p, you get 1 over I. That's what I was telling you. Play with the exponent. So when you take 1 over I raised to p, then what you get is, if you raise it to p, then it will be summation 1 over I, that's infinity. Therefore, this sequence 1 over I raised to 1 by p is not in LP. But if you raise it to q, what you get is q by p. Since q is greater than p, q by p will be greater than 1. And therefore, it will be convergent and therefore it will be LQ. Should I write it and show it? Simple, right? Do you want me to write it? Okay.
No, sir.
All right. So that's a simple matter. So this is this part, this latter part, whatever he has given here, L1 not contained in LP, is proved here. Okay. Now what remains, we have already shown it's a non-linear space. Finally, we have to show only it is completeness. So this is the first major theorem that we are seeing in this course. So let us look at the proof of the completeness. Proof is slightly longer, okay, but it's easier. What do you mean by completeness? We have to show that every Cauchy sequence in LP actually converges in LP. Convergence in LP means convergence in the norm. So you take a sequence Xn, okay, in LP and assume it is Cauchy. Now the ith component of Xn is written as Xin. The ith component of Xm is written as Xin. This I showed you last time, that this mod of the ith component of Xi minus Xin is actually less than or equal to Xn by Xn minus Xm. This is an obvious thing, follows from the definition. So if Xn is Cauchy, then this sequence Xin minus Xim is also Cauchy. Since real line we have assumed it to be complete, so we have assumed complex or the real line is complete. So this Xin as n goes to infinity, for a fixed n, for a fixed I will converge. Please note n and m are moving here. I is fixed here. Alright. Although he has not written here. So you fix I and let the nm go to infinity, then this goes to 0. So this being Cauchy, this sequence Xin, that is the component Xin, x1n, x12n, etc. Or rather x I1, x I2, x I3, etc. etc. is convergent. Since it is convergent, you call the limit as xi. So let xi be equal to limit of n going to infinity xi. You are fixing I here, letting n go to infinity. Now define a sequence x with xi as the ith component. That is the element that we have. Now we expect, what do we expect after all? Since xn is Cauchy, we expect this sequence xn to converge to this x in LP norm. See, there is one thing that we say we expect, and another thing that you prove it. Okay? So there is a motivation is not a proof. Motivation will make you to think of a proof in that direction. Okay? So now we show actually this xn goes to x in LP. What do you mean by xn goes to LP? The norm of xn minus x in the LP norm goes to 0. Okay. So first we calculate that norm. So you see, the problem with L infinite LP or something, it is infinite dimension. It's not finite dimension. Do you all accept it is infinite dimensional? This LP? Yes or no? Why we can't use linear algebra? Because it's not finite. Is it clear or not? Huh? Rishabh, is it clear that it is infinite dimension?
Yes, sir. Yes, sir.
Why? Why? Shall I write it?
Because it is infinity norm.
Hmm? Because yeah, because go ahead.
Because it is infinity norm. That's why.
There is no infinity norm here. It is LP norm. Huh? Shall I write it and show it?
Yes, sir.
See, what do you mean by finite dimension? Take X to be a vector space. Okay. Suppose X is a vector space. When do you say it's finite dimensional? X is finite dimensional if it has a Hamel basis which is finite. Okay? Yes or no? X is infinite dimension if X is not finite dimension.
Yes, sir.
All right? This is the definition. Now, my question is that if it is a finite dimensional space, what is the maximum number of linearly independent? Suppose the dimension is m. Okay. Suppose the dimension is say k. How many linearly independent vectors that X can have at most? Hmm? How many linearly independent vectors can have? At most k, right? It cannot have more than k independent, linearly independent vectors. In fact, if X is finite dimension of dimension k, then any k plus 1 vectors are linearly dependent. You know this or not? You need to have a very, okay? So to show that this is infinite dimension, you have to show it's not finite dimension. That means there are infinitely many linearly independent vectors. So what are the linearly independent vectors for LP? So let us take LP. So what are the linearly independent vectors? Below 1, 0, 0, 0, 0. All right. Second one, 0, 1, 0, 0, 0. Third one, nth one, 0, 0, 1, 0, 0, 0. Okay. This is the nth component. How do you write this vector? How do you write this one? In the sequence form. Delta, yeah. बोलिए जल्दी बोलो. Delta I1. Clear? When I is 1, it is 0. When I is 2, it is, sorry, when I is 1, it is 1. When I is 2, this is the Kronecker delta. This usually you do not it as E1, okay? This as E2, this as En. Dot, dot, dot. Okay? So how do you write this one? This is nothing but the sequence, the Kronecker delta, ith component with 2. So when I is 2, it is 1. If I is not 2, it is 0. Is that? That's what you have. So this, you write it as E1. So how do you write the nth sequence? Nth sequence is nothing but Kronecker delta In. This is the ith component. Okay. ith component of En. Clear? These are linearly independent, that's obvious. How many such vectors are there? Infinite. Therefore, it is not finite dimensional. Clear?
Yes, sir.
You see, what I want to say is that you say something and you give a proof, it's a different issue. Okay? That's what I am saying. If it were to be finite dimensional, xi would have converted to xn would have converted to xy. The reason is that component-wise convergence is same thing as a norm convergence in the finite dimension. But that is not true in infinite dimension. That is why we have to give this proof. So by assumption, there is an n naught greater than n. So xn minus x naught is less than epsilon by 2 if n. This is because the sequence section is Cauchy. And therefore, the component, ith component is also less than epsilon by 2. Okay. That is true for 1 less than or equal to p less than infinity. For p equal to infinity, you will do a similar job. Okay, I will not do that. So for 1 less than or equal to p infinity, what you do is, in this summation I equal to 1 to 1 xim p raised to p. Fix one of them, right? For example, you fix say n and you let, okay, when you let m go to infinity in this one, so what you get is this xi, this is anyway less than epsilon by 2 here. In the summation, this mod of xin is there. Xim goes to xi. So this is what you get, less than or equal to epsilon by 2. For p equal to 1 less than, this is what you have. And you now let n go to infinity, you get norm of xn minus xp less than epsilon by 2, that is less than epsilon. That means the sequence section converges to x in the LP. Clear? So we have shown that every Cauchy sequence converges in the LP. That's the story. All right. The remaining part of the proof is simple. Okay, you read it up. Okay. That show that C naught is complete, etc. It's not a big job. And the major part is that this getting a subsequent sequence which converges pointwise and etc. All right. So that's the proof of that one. The proof of completeness in many cases are similar steps in the above. I have taken more time to give you completeness proof. The reason being that the above proof component-wise convergence, that is xin converges to I for each n, is an important affair. Okay. I'll come to it later. Okay. Now there's a question here. Is it true that if the sequence converges to in LP, then it converges component-wise? Obvious. Suppose it converges component-wise, will it converge in the norm? That's the second question. It is not true. So try to give an example to show that point-wise convergence in LP, that is component-wise convergence in LP, does not give you norm convergence. Try it. Okay. The hint for that is think of a series which you can sum it up, or which you know is convergent. Which is the simplest series that you know which is convergent? Quickly answer. Huh? Which is the simplest series
Sir,
that is convergent, you know?
yes, sir. Yes, sir.
Which one? Which one? Give me an example.
Yes, sir. 1 by n square is convergent series, sir.
Do you know the sum?
Some, sir. No, no, sir. Partial sum, I don't know, sir.
Geometric series, no. 1 plus r square plus etc. etc. 0 less than r less than 1 is convergent, and the sum is 1 over 1 minus r.
Yes, sir.
Use that. That's the one which you have to use. There are only 7 guys here. What happened to others, huh? Rishabh. बाकी लोग कहाँ गए हैं? वो now 10 have come, huh? ये कैसे होता है यार? कभी कभी 7 दिखता है, कभी कभी अभी 11 हो गया. Hey, don't bunk the classes here. It's very important that you should attend the class. Okay. Now, have you studied measure theory? Integration? Lebesgue measure? Hmm? अरे कुछ ना कुछ बोलो. Yes, no. Have you studied measure theory, measurable functions, etc.?
Yes, sir. We are studying in stochastic calculus. Yes.
Not in the real analysis. Okay, somewhere you have learned. Now that's what we are going to do now. Lebesgue spaces. So the Lebesgue space are simply LP spaces. This is capital LP. Okay. Normally, when you say LP, we mean small LP. Otherwise, you say capital LP spaces. Are familiar to those who have done the Lebesgue integration and Fourier analysis. So we only have given the outline here because this is not a course on measure theory. So let X be contained in Rn. Okay, be an open set. Or if you don't want to open set, you take a measurable set. So let U be a map from X to K. That's the domain of U is X and the range is either real or complex. Now you look at the set of all measurable functions U for which the integral over X mod Ux raised to P dx is finite. Whatever the summation that you saw in small LP, that summation will be replaced by integral, right? That's what you have studied. An integral can be actually approximated by summation. All right. So instead of summation, you mod uxi raised to p. Now you have integration over x mod ux raised to p or raised to p. 1 less than or equal to p less than infinity. What is the infinity norm? That is, when p is infinity. Essential supremum of mod ux x belongs to it. Essential supremum means that it's almost everywhere bounded, almost surely bounded if you wish to. So let LPXK be written as, we write it as LPX. We understand what is the scalar, okay? It's a set of all measurable functions for which the integral is finite. Now, this norm, he has already used a norm UP here, will show actually it's a norm, okay? To show that it's a norm, it's a norm on LP, we need 2 inequalities, as usual. Same thing we did in the small LP. One is the Hodder's inequality. For 1 less than or equal to p less than or equal to infinity, if U is in LP, V is in LPX, then UV is in L1, which is written as integral of mod U mod V dx less than or equal to the LP norm of U and LP prime norm of V. What is this P prime? It is a dual index of conjugate index of P. That is 1 over P plus 1 over P prime equal to 1. Okay. P prime in this not here in most of the things, they use it as the conjugate prime. So P prime means conjugate means 1 over P because 1 over P plus 1 over P prime is 1. Okay. This is one thing that we should know. Moreover, these are also the following facts. For 1 less than or equal to p less than, LPX is Banach space. If X has a finite measure, L infinity is contained in LQ, that is contained in LP, that is contained in L1x. Okay. If 1 is less than P, less than Q, less than infinity, if X has infinite measure, these inclusions are not true. These are slightly delicate matters. Okay. So when I come to you, Mizoram, and this month end, I will do it there. Okay. So this, you understand that you know all these things. Okay. You have to show here these terms are, satisfy the Minkowski's inequality, etc. I will send you some notes from some other book. Otherwise, you see the book of Crazy, you have the proof for 7.7 and 7.8. The proof of completeness here is very, very complicated. So I will not do the proof of completeness for capital AP. I will try to do the proof in the month of October end or November if I get that. Okay, all right. What is the next example for bounded continuous? The space of bounded and continuous functions. Okay, so let X be any set, E be the norm, it's a norm space. For example, U from X to E, you define norm of U infinity to be supremum of modulo X. Okay, then we define the space of our bounded functions by BXE, B for bounded, X for its domain, and E for the what is called the range. So U is a map from X to E, and you have norm of U infinity is bounded. Why do you need this X to be E to be a normed space? You are using the norm of infinity here. That's why you need this. Okay. So the completeness of BFE is equivalent to the fact that the uniform limit of bounded sequence of functions is bounded. The proof follows the steps outlined in the remark 7.6, and therefore he is not giving the proof here. Okay. Let me see. So if X is a set and E is a Banach space, okay, then B of XE is a Banach space with a supremum norm. The proof is simple here. Okay. I will try to write it in the known terms. Okay. The problem is that this person is complicating our life, so let us not complicate our life. Okay. This is the what is called the I give you the whole story in a simpler form. You take C01. It's a compact set. Okay. So this is nothing but set of functions from 0, 1 to k, and it is continuous. Okay. 0, 1 is compact, plus f is continuous, implies f is bounded. I will not do this. Okay. This, every country function in a closed bounded interval is considered. So therefore, this norm of f, which you define it as supremum of mod of fx such that x is in 0, 1. This is also written as norm of f with infinity norm. That is a supremum. Okay. This is a norm. That's obvious. 1. Norm f equal to 0 implies and by implies f is 0. That's obvious. If the supremum is 0, okay, so f is 0. Now take the second one. Norm of alpha f is nothing but the supremum of, okay, alpha f means alpha times f of x, okay, such that this happens. That is emptiness, okay. This is supremum of this, okay. Now, mod alpha times f of x is actually mod alpha into mod x, mod of fx. So this will be equal to mod alpha into the supremum of this, okay. Why it comes out? Because this is independent of x. So it comes out of the supremum. So this will be equal to mod alpha into norm f. So second one is also true. Third one, okay, you take f plus gx, okay, that by definition is f of x plus g of x. Okay. Okay. Now you take the mod of f plus g of x. That will be less than or equal to mod of fx plus mod of gx. That is less than or equal to the L infinity norm of f plus the L infinity norm of g. That's because this is infinity norm, supremum. Therefore, fx is. So what it tells you is the following, that you see here, this implies that f of x is less than or equal to norm f infinity because it's the supremum. That's what I am using there. Now this right side is independent of RHS, is independent of x. So that implies now you take supremum. So what you get is norm of f plus g is less than or equal to norm f plus norm g. Okay, so that tells you that this norm, on C01 is a norm. What does it imply? C01 with this infinity norm is a non-linear space. Is it clear? Any doubts on
Yes,
what
sir.
we have written? Huh?
No, sir, no doubt.
Okay. Let's go back to the. So what he uses here, this x he is using here, compactness. Okay. He using the fact that this supremum is bounded. Either you use the supremum is bounded, or you use the fact that he is compact. Whatever you want to do. Okay. And the following proof is there. So what is the proof here? That this x with this supremum norm is a complete nonlinear space. What do you mean by complete nonlinear space? we have to take a Cauchy sequence and show it is convergent. So let UN be a Cauchy sequence in BXE. So point-wise, that's what I wrote now. Point-wise values are bounded by the norm. So UNX minus UMX on E, this norm, the point-wise norm, that's bounded by the norm in the infinite norm. Now this is independent of X here. Therefore, this whatever, if this UN is Cauchy, then the sequence UN is also Cauchy. Okay. Now assume that E is complete. Okay. We assume that E is a Banach space. What we have used there in place of E, we have used the real line or the complex line, okay, or complex number C. Both E, K and A, C are complete. So he's using the same proof. So this since E is complete, so this sequence will converge in E. So define the limit for each fixed x. Define limit n going to infinity of UN x to be U for all x. So what we show now is that this is a point-wise convergence, okay, on for each x. Now we show that this UN is convergent to U in the norm, infinity norm. That's a simple proof. Okay, I will not bother you to leave it here. Okay. I mean, it's an obvious. So let me come back to just 1 minute. Save as this class work too. Okay. Let me save it. I'll send it to you. What I mean is that we want to show this C01 with the infinity norm is complete. Okay. So let UNX. So let me call it as X. Be contained in X, be Cauchy. So mod of UNX minus UMX. What is this? By definition, this is nothing but mod of UN minus UM at X. Clear? These are not written in the notes. And that is less than or equal to its supremum. Therefore, norm of UN minus UM infinity. Okay? This is independent of X. So they could take the therefore, UN Cauchy implies that this sequence UNX is Cauchy. For all x in 0, 1. This is in R. UNX is, what is the C01? It's a map from 0, 1 to K. K is either R or C. So this is a sequence in the real line or a complex line. But this is Cauchy. So K is complete, implies this UNX converges to UX as n-tends infinity. First claim, U belongs to X. Why? Uniform limit of continuous function is continuous. Okay. Uniform limit of continuous maps is continuous. Okay, that's what you are using. Second thing, this whatever you have here, okay, take nm large so that norm of un minus um is less than epsilon by 2. Okay, if nm is large. Why this is true? Because we have assumed this to be Cauchy. Okay, so now you look at unx minus umx. Take this one. That is less than or equal to epsilon by 2. Now you let m go to fix n, let m go to infinity. So this implies that mod of unx minus ux, okay, less than epsilon by 2. Now you let n go to infinity, you get unx, okay. Take the supremum here. What it says is norm of un minus u goes to 0 as n goes to infinity, because this side is independent of x. So this implies that un converges to u in C01. That is your x. Clear? I given the proof in a simpler way. In the case of when this whatever he has given, I am taking x to be C01 and e to be the real complex number. He has given it in an abstract way. Okay, but what we are interested is in C01. Okay, so it turns out that this C01 with the supremum norm is a Banach space, and etc. So that gives you a quick analysis of the major examples of the functional analysis which you should know. So these LP spaces, what I was using here was the one which we used in the distribution theory when I came to Mizoram and gave 10 lectures. Okay. So that is one story. Okay. The second story is about identification. All right. So let me explain to you what I mean by identification. One of the important aspect. Okay. So I'll tell you a small story. One of the important aspect in mathematics is what is called equality. Okay. So when do you say that the two spaces are same or almost equal? So when do you say two vector spaces are same? When you have an isomorphism. Okay. So if you have one vector space m, another vector space n, if there is an isomorphism between m and n, you call it as equivalent spaces, or m and n are identified. In the case of a topology, you talk of homeomorphism. So here it's a homomorphism, here it's a homeomorphism. What do we do in the case of, in this case, when you have a non-linear space? You have a vector space structure, you have a continuous space structure also. Therefore, we need to define a homomorphism or an isomorphism, and we have to also maintain the metric structure. So we have to retain the continuity part. So what do we need here is a continuous linear operator concept. Okay. That is what the next part of the where are the guys here? Rishabh, only 6 fellows are there. What happened to other? Sonu Kumar.
Hello.
कहाँ गए यार लोग? बंद कर दिया तो
पता नहीं sir. I don't know sir. I'm attending from the lab. They are attending from their own laptop and devices.
How do you go about lecturing people? Yeah, if this is the way one does it. Is this the way that the NIE?
Yes sir. I think we have to make it strict every day taking attendance.
Can you take it?
I will take attendance sir every day. After
Tell
that.
them that you have to be strict in attending the classes.
Yes sir.
So I will little scared, but the guys are not attending the classes. Okay. So this is the basic property of linear operators. So we start with some definitions. What is a bounded set? Suppose a subset, you have a non-linear space E and you have a subset U. U is called bounded. If it is contained in a ball of radius, large ball of radius. So you take two non-linear spaces E and F. We define the home of EF, which is set of all linear operators. Okay, people call it as home. Don't worry about the definitions. So set of all linear operators from E to F. Right? It is also written as L of E, such that T is a linear operator from E to F. The linear operator, okay, it is the same thing as how we define the linear operators on. Okay. Just 1 minute. I may have to use crazy book at this book is too fast. Okay. So you have two non-linear space. Say M and N on the same set of scalars. Okay. A map T from M to N is called linear. Same definition that we have. T of x plus y equal to Tx plus Ty. T of alpha x equal to alpha Tx. Okay. This is for all xy in M for all alpha in the same scalars. Okay. Such a map is called a linear map. Okay. So this being non-linear space, there's a topology also. Okay. So T from M to N is called continuous. If norm of Tx minus Ty, this is in N, is less than epsilon. If norm of x minus y in M is less than delta. This is the one. Okay. So this home, what we actually mean is the set of all linear maps from M to N are linear and continuous. This is what is called the notation homomorphisms or home. Okay. How do you write this one? You write it as L of Mn. Some people write it as bounded linear map from M to N. So these are the notations that we have. Okay. It's almost time up. Next time I will do the continuous linear operator from M to N, the equivalent forms of that. I will also send you some notes from somewhere, so that it will be easier for you to understand what this thing is. I probably give you the notes from either Simmons or from the Krajik book. Okay. Any comments? Any questions you want to make? Or say? Any comments?
No, sir.
Okay. Thank you very much. Have a good day. Bye.
Thank you, sir.
See you on Thursday.